Welcome back, Chemistry Theory. This is the third video in the 1.2 electron configurations. We'll try to finish things off here, but hey, we may need a fourth one. We'll see. So we just finished talking about when we fill up the 4s region, we then move to the 3d region. So beginning with scandium and extending through zinc, electrons are added to the 5d orbitals until they are completely filled. Thus, the fourth row of the periodic table is 10 elements wider than the two previous rows. These 10 elements are known as the transition metals or transition elements, and of course they are in the middle of the periodic table. In writing the electron configurations with these, we fill the orbitals in accordance with Hund's rule. We put them in singly before we begin doubling them up. So on the next page here, we have them, so they have one electron each, and then we put the second one in with spins pairing until the shells are completely filled. The condensed electron configurations and corresponding orbital diagrams for two representations are here. So manganese, for example, we would have argon. That would be the lowest noble gas. So yes, we would have, no, I know my table here isn't the greatest, but argon's over here. Then we fill up the 4s one, and then fill up to manganese, which is about right here. So it would be, it's 5 up, so 3, these would be filled. And then we double up. Zinc, again, we fill up argon, the noble gas, 4s2, and it has these ones completely fill in the D region. Once all the 3D regions have been filled with 2 electrons each, then where do we go then? After 3D, we go into the 4p. Yes, so then we go there. And then we reach krypton, which is atomic number 36. Another of the noble gases. Rubidium, then we go down to the 5s region and start filling that up and keep on going. Oh, this should be a capital O here. On the front side, inside, notice that. I'm not sure why that's a capital N. I'll have to fix that. And we'll see this when we get into the next 1.3 section, when we relate it to the periodic table, as opposed to using this as an ordering technique. There's going to be another way, and you'll likely find it to be easier using the periodic table. Now, the lanthanides and actinides, of course, those are the ones that are down here. Now, notice, in this little diagram, yes, we come out of here, so it's like 3D. The F region, F block should be coming out at you. So 6s2, then the F regions, and this is the 4f region. Then we go back to 5d, etc., as we'll see. The 6th row of the periodic table begins with 1 electron in the 6s orbital of cesium, and then 2 electrons in the 4s orbital, barium. Notice, however, that the periodic table then has a break with elements 57 to 70 placed out of the below the main portion. This break point is when we begin to encounter the 4f region. There are 7 of those, and unfortunately I don't have them on this little sheet. So we'll have to take a look at how does that come into play. And we'll look at that more in the next section when we deal with the periodic table, because you can see here, there's a plan here. There's a plan here with the periodic table in terms of the S region, D region, and F to make it a lot easier. These elements are set below. Yes, yes. The properties of Latinite elements are quite similar to the actinides. These elements occur together in nature. For many years, it was virtually impossible to separate them from each other because the energies of the 4F and the 5D regions are so close together. The electron configurations, here's where it gets tricky, and we're just going to touch on this. Sometimes the electron jumps out of a D region into an F region because they're very similar. So there are some considerations that we have to take a look at. So, for example, lanthanum, cerium, and praseodymium, I can't even pronounce it, praseodymium. Look at this, 5s, 6s2, 5d1, 6s2, 5d1, then go to the 4f, and then here 6s2, and then forget about the d, but go into the f. So there are there's quite a few exceptions. In fact, I've taken periodic table and noted some of them here, which we'll take a look at some. So the highlighted ones here are kind of different from what they should be. And we'll maybe look more at the transition ones, and that these ones try to become half full as opposed to being left with the R. And the F region here, you'll see that, oh, there's quite a few here that are different from the predicted electron configuration. So yes, because La has a single 5d electron, it is sometimes placed before symbol Y as the first member of the third series. Ce is then placed as the first member of the Latinites. Based on their chemistry, however, La can be considered the first element of the Latinite series. So you'll see even different periodic tables often start with different elements. So most of the time, this is going to be La and this is Ac, but sometimes it's different. Sometimes you have 15 down here. Sometimes you have 14. So yes, it gets a little tricky when we get down to there. After the Latinite series, the third transition series is completed by filling the d orbitals, etc., etc. This brings us to radon, the heaviest known of the noble gases. The final row of the periodic table begins filling with the 7s orbitals. And again, I didn't even include that with this. In this section, we're just going to look at these. And then 1.3 will kind of tie all of this into each other. And then, yes, this just refers to the bottom F row. The actinide elements, which we have uranium in there, plutonium, and then we complete the 5f orbital region. The actinide elements are radioactive and the most part are not found in nature. So we'll stop there, folks, and you should be able to do the assignment there by simply following this ordering scheme right here. So using the ground state electron configuration, we're showing all of these fillings from 1s all the way up to however far we go. If we're doing the noble gas notation, or the shorthand version, let's say I was using an element that's in the 3s region. So let's say, for example, magnesium. I would say, okay, the electron configuration for magnesium is, okay, neon in square brackets, and then, let's see, there's 2 electrons there, so 3s2. All right? So we'll end it off there, folks. And yes, we'll do the section 1.3 next, in which we look at the periodic table and see a better scheme for knowing how to do this.